Welcome back, friends. The topic of today's lecture is stator design of three-phase induction motor, and in this lecture we will discuss the design of stator winding, design of stator slot, stator teeth, and depth of stator core. First we'll discuss about the stator winding design. The stator winding design is nothing but the decision regarding the total number of turns required and the size of the conductor. Now normally the turns required calculated as turns per phase. So it means how many turns are required in one phase. And once you calculate the number of turns required in one phase, then you can easily calculate the total number of turns required for n number of phases. And the turns per phase is denoted by Ts. And as we know that the EMF equation of three-phase induction motor is Es is equals to 4.44 kWf into phi into Ts, and from this equation we can easily calculate the Ts is equals to Es divided by 4.44 kWf into phi. But in most of the time in the examples the phi we need to be calculated. So phi is unknown parameter, and this phi is calculated from the given value of the specific magnetic loading. As we know that the specific magnetic loading BAV is equals to P phi divided by pi dl, and the BAV is usually given in the example, and if it is not given we have already discussed how to assume. And the D and L are the main dimensions, so it means once we calculate the main dimensions we can go for the Ts calculation. So from this equation phi is equals to BAV into pi dl divided by P. So by using this equation we calculate the phi value, and then we will put this phi here in this equation. And if we assume the full pitched winding, then for the full pitch winding, as we know that the Kw is 0.955. So by after the assumption of the Kw and the calculation of the phi, we can calculate the number of turns per phase Ts by using this equation. Then how to calculate the size of conductor? Size of conductor is nothing but the conductor cross sectional area, and this cross sectional area is calculated by using the current density equation. As you know that the density is the ratio of the quantity divided by area. It means for the current density it is denoted by del, and del is equals to current I divided by the area. So in this case we need to calculate the area of the stator conductor, so we require the stator current density, so it is denoted by del S. Stator current is Is, so we will get the area of the stator conductors, and from this equation the area of the stator conductor As can be calculated as As is equals to Is divided by del S. And Is is calculated as kVA into 1000 divided by 3 into Es. Now the kVA into 1000 is VA divided by 3 into Es. Es is the V, so the V gets cancelled, and you will get the Is, that is the stator current, in amperes. And remember the usual value of the current density del S is 3 to 5 ampere per millimeter square. So it means if the current density is not given in the example, then you have to assume the current density between 3 to 5 ampere per millimeter square. And normally we are assuming the 4 ampere per millimeter square current density. So normally we are assuming the value of the current density del S is the 4 ampere per millimeter square. So with this assumption you can calculate the size of cross sectional area of the conductor, that is AS. But if it is given in the example, no need to assume, you have to take the given value. Now the next is the stator slot design. Now in the stator slot design, we need to discuss about the two things again. First, how many stator slots are required to house the winding, and in every slot how many conductors we have to be insert. So that means the number of stator slots required and the number of conductors per slot. Number of stator slots are denoted by SS. And remember, there is no fixed rule for selecting a number of stator slots. And in general practice, for a common design, usually the 3 to 5 slots are selected. 3 to 5 slots are selected for slots per pole per phase. So what it means? 3 slots per pole per phase. Suppose if we select the 3 slots per pole per phase, it means for one pole, one phase we require 3 slots. Suppose for a machine, you want to be design a machine for the 4 poles and 3 phases. So how many slots are required? If you take the 3 slots per pole 4 phase, means for one pole one phase 3 slots are required. So 3 into, for one pole 3 means for 4 poles into 4, and for 3 phases into 3. So if you calculate this, you will get 36 slots. So if you choose the 3 slots per pole per phase, and if you want to design a 4 pole 3 phase machine, then you require 36 slots. So in this way you can calculate the total number of stator slots. Then how to decide the number of conductors per slot? As we know that in every turn there are 2 conductors, and the TS is the total turns in one phase. So if you multiply by 2 here, it becomes the total number of conductors in one phase. And if you multiply by 3 here, it means it is the total number of conductors in all 3 phases. So the total number of conductors in all 3 phases is 3 into 2 into TS. Then we need to decide the number of conductors per slot. Suppose from this equation 3 into 2 into TS, if you get the total number of conductors are 100, then how many number of conductors in the one slot? So just divide by the number of slots, and number of slots are SS. So the total number of conductors per slot, which is denoted by ZSS, it is calculated as ZSS is equals to 3 into 2 into TS, which is the total number of conductors divided by SS, that is the total number of slots. So we are getting a total number of conductors in one slot or the per slot. Also you can calculate the size of the slot by using this equation. The ZSS, that is the conductor per slot, into AS, that is the cross sectional area of the conductor, divided by the space factor. And if the space factor is not given in the example, then usually the space factor varies between 0.25 to 0.4. So if it is not given in the example, you can consider any value for the space factor between 0.25 to 0.4. Now let we come to the stator teeth design. Once the slot dimension is decided, then it becomes fixed. So once we calculate the dimension, that is the size of the slot, it becomes fixed. But we need to check whether the calculated value of the size of the slot is maintaining the flux density in the range or not. And usual range of the flux density is 1.3 to 1.7. So it means whenever we are calculating the size of the slot, that size of the slot should maintain the flux density between 1.3 to 1.7. If the flux density is going beyond this value for calculated value of the size of the slot, then the calculated size of the slot is wrong, or you cannot choose. So that's why, so whenever we decide the size of the slot, that size of the slot we need to check with this value of the flux density. And it is how we are checking that the flux density in the teeth is denoted by BTS, flux density in the stator teeth, and that is equals to phi divided by tooth area per pole. And that you can also calculate by using this equation, phi divided by number of teeth pole into number of net iron length into the width of the teeth. As the number of teeth poles are total stator slot SS divided by number of poles, the net iron length is Li and width of tooth is WTS. So you can use the expression for calculating the BTS. The BTS, that is the flux density in the stator teeth, is equals to phi divided by SS divided by P into Li into WTS. So where is the length and width is nothing but the size of the stator teeth, and just to check that size of the stator teeth is giving us the flux density in this range or not. Now the depth of the stator core. The depth of the stator core is denoted by DCS, depth of the stator core. Now how to calculate this depth of the stator core? So just for that purpose I have given here the cross sectional view of the stator core, and in this figure the DO indicates the outer diameter of the stator core and the D indicates the inner diameter of the stator core. And if you see this diagram, then it is very easy to understand. If you calculate the length, DO minus D is equals to, now the DO minus D is equals to, so this much is the D and DO is the outer periphery, outer diameter. So DO minus D is obviously this distance plus this distance, and these two distances, this and this, are same. Now first we will calculate this value. So if this value is equals to DSS plus DCS, where the DSS is called as depth of the stator slot and DCS is the depth of the stator core. It means this length is also DSS plus DCS. So it means the DO minus D is equals to this DSS and this DSS together becomes 2 DSS plus this DCS and this DCS together makes 2 DCS. So we are getting the equation DO minus D is equals to 2 DSS plus 2 DCS. So you can see here in this equation 2 DSS plus 2 DCS is equals to DO minus D. So we can write the equation as DO is equals to capital D, that is the inner diameter, plus 2 DSS plus 2 DCS, and from this equation we calculate normally the depth of the stator core, the TCS. Further in detail how to calculate the depth of the stator core we will discuss at the time of example also. Now I hope you understood the design of the stator. Thanks for watching.